In the first video, I taught you a little bit about vectors. In this video, you're going to be learning how to add and subtract one-dimensional vectors. These are collinear vectors, where collinear is a term referring to points along the same straight line. So when we add one-dimensional vectors, points are along the same straight line. Now, we're going to get what is termed the resultant vector. The resultant vector is denoted with a capital R, and of course you see the vector symbol or arrow above the capital R, which is often used to represent vector quantities. Let's look at these two vectors here. We have a positive 3 meter vector and a positive 1 meter vector. Again, these include both direction, denoted with the positive signage, and magnitude, proportional to the length of the arrows. If I move the 1 meter vector in such a way that its tail aligns to the head of the first vector, it becomes readily apparent that the resultant vector, or the sum of these two vectors, is equal to a positive 4 meters. This can be expressed as A plus B equals C, where C is the resultant vector. This is termed head-to-tail vector addition. As I've just shown you, when using head-to-tail vector addition, you will simply align the head of the first vector to the tail of the next vector. In this first case, the vector positive 1 meter that was being added to the first vector. That's exactly what I did to solve for the resultant vector of positive 4 meters. Now, what about if you're subtracting vectors? Well, when subtracting vectors, you're actually going to reverse the direction of the vector being subtracted, and then you're going to add it to the first vector. This can be shown as A minus B equals C. That's going to give you your resultant vector. However, we're going to take our second vector, in this case denoted with a B, and we're going to reverse its direction. In other words, we're going to reverse the signage, and we're going to add it to A. So this can be expressed as such. Now let's look at an example here. Here we have a positive 3 meter vector, and I'd like to subtract a positive 1 meter vector. Well, we're going to take the positive 1 meter vector and we're going to reverse its direction. Then we're going to use head-to-tail vector addition to align this second vector, which has now been reversed. We're going to align its tail to the head of the first vector, and then it becomes pretty obvious our resultant vector is going to be a positive 2 meters. Here are some other examples. Here we have a positive 3 meter vector and a negative 4 meter vector. So pause the video for a minute and see if you can use head-to-tail vector addition to find the resultant vector in this example. As you can see, when I align the tail of the second vector to the head of the first vector, the resultant vector in this case is negative 1 meter. A student stands on top of the bleachers and throws a bocce ball straight up in the air 3 meters, and then it comes down, falls 12 meters down to the ground. What is the resultant vector? We're going to always represent these graphically. That's what vectors are. So let's go ahead and take a look here at the magnitude and direction of the first part of this problem, 3 meters up. Notice I'm using relative directions, which I taught you about in the first video. What happens after the bocce ball goes 3 meters up? It comes 12 meters down. So I have two vectors here that I'm going to be adding up. using head-to-tail vector addition and aligning the tail of the second vector to the head of the first vector, I can solve this problem to find the resultant vector is negative 9 meters. Now, I purposefully switched to signage to reinforce the idea that it is permissible to use negative 9 meters to denote 9 meters down. But you would not say negative 9 meters down. So I'm showing this here in this problem to reinforce concepts I discussed in the first video. So the answer, 9 meters down or negative 9 meters. A deer walks 10 meters east to a patch of clover. It then walks 15 additional meters east to a creek. The deer then turns and runs west 25 meters. Find the resultant vector. All right, so let's see what we have here. We have the deer moving 10 meters to the east. I'm using signage to show that. The signage plus is east, negative is west, and the length of the arrow is proportional to the magnitude of the vector quantity. Then it moves an additional 15 meters to the east. Last, it moves 25 meters to the west. I've used a negative sign for this third vector. Now we're going to use head-to-tail vector addition. In this case, we have 3 vectors. We'll align the tail of the second vector to the head of the first vector, and then we'll follow that same methodology for the third vector. And in this case here, it becomes very obvious that our resultant vector is positive 25 minus 25, which gives us an answer of 0 meters. Now, I wonder what would have happened if the deer would have turned and sprinted 15 meters at 20 degrees north of east. In this video, we continue to lay the foundation to get you ready to add vectors in AP Physics 1. And I'll see you guys in class.